We are in the age of just let the AI assistant do that for me. And by that, I usually mean process my natural language input, detect my intention, figure out what actions need to be taken, maybe communicate with other agents through the same MCP framework, decide what needs to be done, use a series of tools and commands that I've outlined for you as a series of functions, determine which ones needs to be accessed, communicate between each other, perform semantic search by going through private and public data sets that I've probably curated for you, determine the relevant articles and information to retrieve, to summarize, to maybe run some formulas, calculations, functions, put all the information together, create a short and sweet message, and tell me what the answer is. Well, all of that is possible through a combination of very buzzworthy acronyms. In this video, we're going to break down and explain what is an LLM, RAG, AI, Agentic, MCP, framework, GPT, and all of the above, how they fit into the same architecture, which of them do you need, which of them do you not need, have a very clear understanding of what they mean and their limitations and key benefits. And after that, hopefully you'll be an expert at acronym bingo and figure out what you can use within your organization. Hello, I'm Iulia from Elastic, and in this community video, we're going to go over all the necessary information you need to become an expert in the new agentic AI space. Let's get started. Now, this video is going to be quite long because there's quite some stuff to get through, but we thought it works better to have it all together if you prefer it that way. However, we're also going to be releasing short videos on each of these concepts. So if you know someone who wants to get a quick and easy definition of any of these concepts in a few minutes, we'll link to that below. We're going to break this down into 4 main chapters. First, LLMs. How can you use these models? What can you do with them? What type of models there are and how they can be really powerful on their own. RAG. We're adding retrieval and generation into the same architecture and using your own private data to do really interesting stuff. Agentic RAG, when we start introducing the agentic framework, having tools and agents that start to think by themselves, take actions, and have tools available to them to still do the things we've seen in the previous phases, but with more initiative. And 4, MCP, which is a framework that allows agent-to-agent communication, as well as makes it more standardized to use different tools, to use different providers, to have a marketplace for all these actions, and basically where we're probably heading into the future. So let's get started with number 1. What are LLMs? Large language models. They fit quite neatly into the data science, ML, AI, fuzzy Venn diagram that you'll see a lot of variations of. And basically, they're the cutting edge of what we can do with natural language processing, or NLP. There are models that understand human language and are able to generate language of their own. Now, just because LLMs have become really popular recently, it doesn't mean that they're new to the scene. As you'll see from some of these graphs as well, they've been around for quite a while. And for someone who has actually studied data science around 2015, back then it was an emerging focus within the machine learning community, focusing on processing text in a way that machines can compute, because basically with machine learning you usually deal with numbers and vectors. Well, there are quite a few techniques that are able to transform sentences into words, either as a bag of word, where we count the number of appearances of different words in a text, something as TF-IDF, term frequency, inverse frequency, that looks at the frequency of word, so that common words such as and or can be taken out of context because they don't have a lot of semantic meaning, and really focusing on unique words. The more unique words in a text are probably what determines the topic or the interest of that text, which makes it possible to search. So looking at appearances of words in different parts of texts, processing a lot of text, such as the Wikipedia pages and other really large data sets that have become publicly available. We have created these models that are able to understand how words are related to each other, how perhaps to mimic grammar or correct sentences, and eventually turn up to create their own blogs or their own exam questions or their own emails in a way that looks almost human, but perhaps still has that quality of imitation to it. The LLM field is also quite vast in terms of what these models can do. We focus a lot on generative language, which we'll cover in most of this video, but it's important to note that other NLP techniques exist, such as sentiment detection, where they can tell if a review is positive or negative, named entity recognition, which was a very important turning point as well, figuring out which entities in a text are actually names or addresses or something that should be hidden away, such as PII data. All of these models are useful on their own, but they're also combined and put together to create the really advanced models that we'll see later on. But it's important to know that they each have value on their own, and for a lot of use cases, it's still something that is worth looking at before you apply a really general mastermind AI model. Also, a key point here that links LLMs with what will later transition into the RAG phase is vector and semantic search. So just as I mentioned, there's techniques to turn natural language into numbers, and most of the time those numbers are vectors, something that you probably remember from school. We would have the X and Y axes, and if we have a 2D point such as house prices and square meters, a classic example, we're able to plot those data points into a 2D space, into a 3D space, and so on and so forth. If we have a multitude of dimensions, it becomes a really complex vector space that we can't really visualize with our human math understanding, but computers are able to process really fast. This allows us, like we mentioned, to have the understanding of closely semantically related words. To give a very 2015 example, we had the idea that king and queen might be together in the semantic space, but we also had operations such as king minus man plus woman equals queen, which is a very rudimentary understanding of how language works and how those words are related, but something that really helped machines progress towards this NLP space. Now, once you understand the vector space and what we call embeddings, which is transforming these words into a vector point that is able to exist in this multidimensional area, we're also able to do searches. Let's break it down visually. Starting with a text you'd want to search through, we first split this into various chunks. These can be a few words, a sentence, or a paragraph, depending on what model you're going to work with. Each model has a context window, which is defined as the number of tokens the model can take in or process at one time. And a token can be a character or a word, depending on the model. You want to make sure that the chunks are about the size of the context window for maximum efficiency. Each model is also designed for a specific task, so you want to make sure you use a model that is appropriate for your project. These can be question answering models, recommender systems, or similarity search. For similarity search in particular, we have embeddings, and these can be of two types. First, we have dense embeddings, where each chunk becomes a vector with a lot of small values representing weights for each dimension. These can be very good at capturing semantic similarity and meaning, but it can be quite computationally heavy to work with due to their large size. On the other hand, we have sparse embeddings, which are based on term frequency. At the most basic level, we have lexical or term search that just represents the presence of a word by a 1, and all other values are 0. This allows us to search for things a lot faster later on by doing a lot of the processing in advance. For example, if we look at how these look in Elastic, turning a sentence into a dense vector gives us a lot of values, and the sparse embedding generated by LSER shows us the similarly close terms already stored in the inverse matrix that will allow us to search later. Once we have our vectors generated, we can put them in the same vector space, which then allows us to interpret the distance between them. Using cosine similarity, we're able to see that closer vectors will have a small angle, opposites will go in different directions, and the rest will be unrelated words. There are different math formulas to use here, but cosine similarity is the most popular. So to put this in action, when we look for something new like API specification, we first use the same model that generated all the other embeddings to also turn this text into a vector, so we can plot it in the same vector space. From here, it's a lot easier to retrieve the closest neighbors, which will be the most similar other chunks. Using semantic search, we're then able to understand things like acronyms and to see the words that are closely correlated because they usually appeared together in the rest of the text. On the other hand, using the classic term search can also very quickly give back very accurate results. So most techniques nowadays use a hybrid approach, taking the results from both different methods and putting them together with some boosting, such as re-ranking. And that is how vector or semantic search works. Which brings us to our RAG chapter, Retrieval Augmented Generation. By now, most of us have probably interacted with the generative AI model. Especially in the case of AI assistants and chatbots, we all know how they work. You ask them a question, they come up with a reasonable, human-sounding answer. However, they do have some limitations. Although some of them have gotten a lot smarter, being able to, for example, look stuff up on the internet themselves, which we'll see in the next episode, for now, most LLMs are still trained on a particular dataset. So they're limited in the types of questions you can ask them. So if you use one of the really big LLMs released on the internet, either open source or through a subscription, they will have a certain context that they're aware of. So if you look for meeting notes from a meeting that you've had and have taken notes on your computer, it's not going to get anything back for you. But there are a lot of use cases in which you would like results from your local data to be included into your searches. Or if you ask a question about what does HR have to say about my reimbursement policy, you could find internet results about HR policies in general, but you will not find the specific ones from your company. That is where Retrieval Augmented Generation comes in. Rather than taking a really large LLM and giving it a lot of your own personal data to train on so that it learns that context, which might have some privacy concerns as well as be really heavy in terms of computation, resources, time, expenses, and usually not necessarily worth it to fine-tune your own model in most cases. So what we then do is we separate the problem into two parts. We run a semantic search, which we've just defined, on our own private data, which is able to retrieve the best results, the best documents, the best chapters or sentences or chunks of the documents that we're looking through. And then with these in mind as context, we can then generate a response to a particular question using a different LLM. So you have, on one hand, your private data that has been retrieved, and on the other hand, you can use this data to generate an answer. But if the model that is used for generating the answer is hosted locally, or it's not a general knowledge model that takes a lot of space to run, then you can still keep the privacy and the security aspect of looking through your personal data. So RAG is a solution that allows you to use the best of semantic and vector search, as well as generate answers. Right? So if we only had semantic search, we would get bad results and give you the document or the reference that your answer is in. But if you want the results to just be a summarization of that or just a sentence, then the generative part will then process that information in the context into a very neat answer. Let's break this down again. Once again, it all comes down to large language models. While in the previous sections we've seen embedding models that are used for vector and semantic search, we're now taking a look at generative models, specifically for text generation. As the name implies, these models are used to generate new text. They do this by building sentences one word at a time. We take a look at the possibilities and probabilities for every word that comes next, analyze the options, and determine the most likely candidate. You're also able to tweak the behavior of these models by messing with features such as temperature, which determines how creative or reliable you want this model to be. However, if you have already interacted with these generative models, specifically to do question and answering chatbots, you may have already run into some of their limitations. First of all, we cannot expect these models to have awareness of the latest information that came out or any sort of data sources that were not included in their training data. They are frozen in time and they are frozen to a specific domain. This also means that they will not have access to your private data or any external data sources, which is probably a good thing, but this limits the subject of the questions you can ask. However, sometimes these models compensate by this by just coming up with their own answers, which we call hallucinations. This makes it difficult to use these kind of models, although powerful and useful, to ask questions when we reliably need an accurate answer. However, as we've seen, semantic search can be used to retrieve very accurate results from defined data sources. So we can try to put these two forces together. Looking again at the API specification example, you look for a term in your data, and with a combination of lexical and semantic search, you can get back all the relevant results based on keyword searches as well as the embedding space and finding similar results from the same context. So this section already brings together all the relevant data that we would need to answer a question. So what we can do is we take this as the context window for our LLM and we provide it as additional information. This allows the LLM to not only use the general data that it was trained on and the baked-in logic that it has, but also reference the data that you provided and making sure that the answers are based and grounded in the information that you wanted to look at. This puts together the ease of interacting with our data by simply asking a question and getting a result, while we can rely that the underlying search was relevant and accurate, and we know that we can trust the results. Putting this together, we get Retrieval Augmented Generation, or RAG. Now, RAG already solves a lot of issues, and you've probably seen it going around the internet. It's a really great process that brings together search and LLM generation, but we're also able to go further than that. So say if you want to use it into the context of a chat, which is what most people do these days, you want to ask a question, behind the scene, the agent is probably going to retrieve the relevant documents and generate an answer for you. However, if you have a follow-up question or you want to use that information and look cross-reference to something else, or you want a colleague to ask the same question tomorrow and get the same results, or based on that information, you also want to create an Excel sheet and run some spreadsheet calculations, you will run into some limitations. Which brings us to Agentic RAG. This combines the best of retrieval, so search, semantic search, vector representation of words, plus generative part of the process, which is generating a nice response or having large LLMs in the loop that can process information, summarize it, and provide natural language outputs. But we also want to take more actions. We want our agents to have more toys. So if you think of the retrieval part as just one tool that the agent can use, we also want to add alternative tools. So besides getting back the relevant information, maybe we want to summarize it, we want to get back some numbers from an Excel sheet or from a SQL database, and we want to run some operations like get a quarterly earnings report or set a calendar invite for the people I mentioned in the meeting, set up a to-do list for myself, whatever it may be. You want more of that AI initiative in the loop. So we're now starting to create more complex architectures. We can define each of these tools that the agents can use, such as the search tool that perhaps if you're based on Elastic, you're able to look through an index, generate a query in full JSON language or SQL, ESQL, whatever it is that your agent wants to use across a database that it probably has permissions to. You can define the way that the agents connect to those data sources. You can define what sits into those data sources and how the information gets retrieved. You can then define what operations can be run on that data, such as a semantic search element, which is very similar to the RAG example that we've been talking about, but you can also give it tools to check external information. For example, get the weather from a particular weather site, get flight information from a agent traveling site, and put all of that together to create an itinerary for your journey. So to break it down one more time, we are first using the concept of vector and semantic search, which enables us to use LLMs to retrieve the relevant passages or documents from various data sources. We can combine this with the generative model to generate natural text as the answer based on these passages we've retrieved, as well as other data sources. However, this process still depends on us creating the right queries or choosing the right strategy for retrieval as a combination of semantic, lexical search, a hybrid approach, and also doing the prompt engineering ourselves, supplying the right prompt and instructions to the model alongside the context that we've retrieved. When we introduce agentic workflows, we move over these responsibilities to the agent. So now the retrieval becomes a tool that the agent can run by itself. Not only that, it can also generate the queries in whichever language necessary. It can also do the same process as a different tool to run a live search to an external data source and gather more information besides the data sources that you initially provided. And it can also run a variety of other tools, from calling various APIs, running plugins, executing small code snippets, making calculations, sending messages, or even generating graphics. All these tools then together can be used to collect a lot of information and then generate the answer based on that. And finally, this is not a one-time command, but rather it can be introduced in the context of a conversation where there's back and forth. You can ask follow-up questions and you can watch the agent think through solving an entire problem by running all these tools in sequence. Each of these tools can be defined in various pieces of code that can be provided to the LLM. It is the LLM's job to choose which of these tools to run and in what order, so you don't have to hard code the entire logic of the process, rather rely on the LLM's understanding of what needs to be done and detecting the intent and the necessary next steps. And this can be continuously expanded upon. The agent can have a few or a lot of tools available to choose between and to run. You can do these sequentially or in parallel. And you can even introduce multiple agents that each have their own specialty with their own set of tools that can collaborate together and put all this information in one place. So the more and more actions we would want to run, the more it could be that we're not creating all these functions ourselves and defining them with our own API specifications. So in the case of the search, we're defining how to find an index, how to run a query, and how to get the results back and how to display them. But we can create this set of steps for a lot of different other tools and services. Now, as you can probably imagine, you wouldn't implement all these from scratch, but plenty of providers that are now adopting agentic processes are creating their own tools. Can we make sure that all these tools, however, work together? And that's where MCP comes in. MCP, Model Context Protocol, does pretty much what the name says, provides the right context to your models and defines a protocol that is uniform and allows you to create compatible various agents or various tooling that should be able to all work together seamlessly. It's been described as the USB-C connector to a bunch of agentic world models or providers. So it allows you to have a standardized way of using other people's tools, other people's agents in a sort of marketplace. So if we look at what we've discussed before, we can still use semantic search as a function, but we can define the way an agent can perform semantic search with the MCP standard, allowing us to give any agent the capability to perform this search or to perform RAG, basically, by retrieving information and using that for generating an answer, but using the same standard so that if another provider has a really good tool for checking flights, you can also use the tool from the MCP marketplace and introduce it into the same architecture. So what we're seeing is that a lot of different providers are creating MCP servers, such as the Elasticsearch server, that would then allow you to perform various actions with a set of functions and tools that have been defined with the same protocol so they can easily work together. This allows you to work with a lot of different data sets without having to define how to connect to those data sources, how to run searches or how to get data from them, how to interact with them, where to put the results. Each of these should be defined with the same MCP standard so that through a few calls made by your agents, all the data should be collected together. This allows for some really complex and interesting applications, using different tools from the marketplace and interacting with different data, from data on your Garmin to data from various public applications or websites that you can search through and combine and create these really insightful AI assistants that know the data sources that you give them access to and can evolve over time. So if you see a new function, a new data source, or a new action that you want your agent to take, if it's defined with the same MCP protocol, you can just add that server into your application and you should be able to grow the capabilities of your agent. And lastly, you should also be able to have different agents communicating together if they use the same protocol. So you can define an agent that does your travel booking, a different agent can manage your agenda, but they can work together to make sure that you have a time slot available, or another agent can summarize and send emails for you. All of these agents can and should be able to work together, or you can have a different strategy of having one master agent that does everything. But as we've tried to mention at every stage, there's of course a lot of fine tuning that you can do, and different strategies work for different approaches. The important thing is that you have the flexibility to choose. And let's use our graphics breakdown one final time. We're going to go over the same example that we've also addressed in a blog and video before, and you'll see this linked in the resources below along with our other supporting documents. This showcases the MCP architecture that relies on the client and server pillar. The client, of course, refers to the user interface you're interacting with, in most cases a chatbot of some kind, and the server is the one where we define all the tools and prompts and resources that can be called into action when the agent determines that they are needed. In this case, the user interface or the client was Claude, which is a popular chatbot, and we were able to call in the Elasticsearch server, allowing us to have a very simple text request that then brings us back the result of a complex query. At the surface level, this just looks like user makes request, MCP client comes back with a list. But what happens behind the scene is a little bit more complex than that. First, we're calling out to an LLM that allows us to determine what the user actually wants by breaking down the prompt. Then getting this back to the client can decide, okay, this is an Elasticsearch problem, so we're going to call out the Elasticsearch server and take it away from here. The server then makes various calls through Elasticsearch with the tools that we've defined, such as finding the available indexes and determining that I need to look at orders, figuring out the mapping of this index, which then allows us to build the query with the filters that we've requested, orders over $500, the past month. So from here, we can also use an LLM to further determine what that JSON request will look like. So we can build out the complex Elasticsearch query, get all these responses back, and use a generative model to put it into a nice answer. So then the complexity is hidden away and the agent determines which steps to take by itself. The user just gets the response back in a very neat way. So let's look back at the example we mentioned in the beginning and see how we understand it now. If you want an AI assistant to just do something for you, you have to have an agent that is able to run tools and commands for you. Part of these commands is probably going to be some form of retrieval. So you're going to have a defined way of connecting to an Elastic cluster, running a query on an index, a query that you're able to generate yourself with an LLM. You get back documents that are relevant. You retrieve them. You get the specific passages that you want. An LLM with generative capabilities can create an answer based on the information that you've gotten back. You can run various other tools to connect to other data sources, check public websites through APIs, collect information from private data, public data, run other commands to get information together, and then put that all into the answer that is provided to you. And if you have the agentic workflow, you're also able to go back and forth and ask questions, have history of the conversations you've had, and are able to ask about things that you've discussed previously. So the agentic workflow allows you to go back and forth and automatically trigger other commands and have the agent take initiative. And if you want to combine this with other tools and other agents, using a protocol like MCP would also be useful, because then everyone can communicate the same language. So you don't need to, from scratch, define all the ways that the agent should connect to a particular database or run a command or ask a question to another agent and process the response. So that is how you can use LLMs, RAG, Agentic, and MCP all together to just create a really useful tool that can automate a lot of tasks for you and very quickly process information from multiple data sources into one. Hopefully that gives you a pretty clear picture of all these acronyms and where they fit in. If you want to go more in depth, in the description below, I will link a lot of articles from our Search Labs blogs that go into more in depth on the various techniques I've mentioned, as well as some of the example I've given. So you can give a read to that, try some GitHub examples by yourself, and build an application to test all these concepts out. Hope this was helpful, and we'll see you in the next video.